ahead with the technical talk of today. I invite Professor Meeker to present.
So it's not very often I have an opportunity to give a talk without any formulas. That's what I'm trying to do. Actually, there's a couple of formulas, but they're in the slide that I borrowed from somebody. Reliability disasters are serious things in many cases. And during my entire career, I've been a student of reliability disasters. In some cases, I've been directly involved in the aftermath. That is, looking at data and applying statistical methods to better understand what happened and how to avoid these problems in the future. So, here's an overview of one talk. I'm going to start out with a definition of reliability. What exactly is reliability? And from there, I'm going to talk about a couple of sort of generic problems that sometimes arise. And then I'm going to go through discussion of some particular examples. So I've got 5 examples that I'm going to talk about in some detail, and 2 others, maybe if I have time, that I can give you a little bit of information about. And along the way, I'm going to try to provide some discussion of some of the things we've learned from these issues over time. So what I say here on the slide is, what have we learned? So what is reliability? Technically, if you open up a textbook on reliability, you'll find a definition something like this. I don't usually read my slides, but I'm going to read this one. So technically, reliability is a probability. It's the probability that the system or vehicle, machine, device, whatever it is that you're focusing on, it's the probability that that device will perform its intended function under encountered operating conditions and for a specified period of time. So this is the definition that Luis Escobar and I chose to use in our book. We had a reviewer who asked the question, why are you using the word encountered here? Because most textbooks would say under specific operating conditions. The reason we used encountered was to emphasize that in the real world, reliability depends often critically on the environment in which a product or system resides. Another definition of reliability is quality over time. So in industrial statistics, quality and reliability are 2 different subjects, but they are linked together. And the way I like to think about the linking is that we can often measure quality. There's lots of different definitions of quality, but think of a customer having a product and they're happy with the product. So that's one definition of quality. And then reliability is that the customer will remain happy with the product over time, that the product will not fail. And I define the term product very generally. It could be something like a cell phone or an automobile, or it could be an aircraft, or something else that we use. Another very common definition of reliability from an engineering point of view is failure avoidance. So a lot of reliability engineers, they think of their job as being, how can I manufacture this product and keep it from failing? Reliability also is a very highly quantitative engineering discipline. So I'm a statistician by training, and virtually all of my applications work and research has been in the area of engineering applications. And perhaps 70% of that has been in reliability. And so as a statistician, I've worked with engineers to help apply statistics and probability to their reliability problems. And I've learned very much over the years in those collaborations. So here's a discussion of a common problem that I've seen arise over and over again. And I've gotten directly involved in a few of these. So a product has been introduced into the field. Maybe it's a new design for a laptop computer. And after some period of time, maybe 6 months or so, suddenly there's more returns than had been expected. And then everybody begins to say, oh, what's going on here? And I might add that in some companies, they develop systems to discover these problems as early as possible, so that they can fix the problem early before it gets to be more serious. If there's a serious reliability problem, eventually everybody in the company is going to know about it. But if you can detect it months early using appropriate statistical methods, that can be very valuable. Usually these failures arise from a failure mode that was unanticipated. That is, the engineers never thought that the product could fail in this certain way. But they've got all these failures coming in. And so the next question is, do we have a serious problem here? And to answer that question, they need to know, well, how many units are going to fail? What proportion of our units are susceptible to this failure? And that will occur during the technological life of the unit. Can we identify a subpopulation of units that are the ones that are going to fail? So in one application, we figured out that it was 1 month's production that was bad. Everything else was fine. And then we could focus on that 1 month to solve the problems. But unfortunately, in other situations, when we go to investigate, we find out that all of the units that have been manufactured are going to be susceptible. And I'll give you some examples of that. And then the question is, how fast will they fail? Okay. And then what's the risk? That is, how much is it going to cost, usually in terms of warranty or the intangible unhappy customers. The other question that sometimes we have to ask is, should there be a recall? So if the problem is a safety issue, where people could get hurt, then in the United States there's a process. And the conclusion of that process might be that we have to bring all the bad product back to prevent people from being hurt. And then how can we fix the problem? Generally the engineers, once they understand there's a problem and they know what the problem is, the engineers can figure this one out. But along the way, the statistical methods can often help. And then very closely related to that is, what lessons do we learn to prevent the same problem from occurring in the future? One common element that I often see in a reliability disaster is that there are multiple mistakes that are made along. Usually engineers are smart enough to make things robust to a mistake, or maybe even a couple of mistakes. But sometimes if there's multiple mistakes, then you can get one of these serious problems to arise. I've written down here some mostly well-known reliability disasters. I'm not going to spend much time on these. You can go to Wikipedia and find articles on every single one of these that give a lot of information. As I said, I'm going to give you details on 5 to 7 other reliability disasters. And how did I choose which ones I'm going to talk about today? Well, first of all, they have some statistical content. I'm a statistician, that's what I get involved in. In some of these, I've either been directly involved, not these, in the ones so you have a chance just to look at these. I want to say just a couple of words about a couple of these. The common aircraft failures, again, there's a nice Wikipedia article about this, was in the infancy of the aerospace era, 1953. And what happened, there were 3 different common aircrafts that all crashed because of what's known as fatigue failure. Well, most engineers that I know understand a lot about fatigue because it's a very important failure mechanism. I had meant to bring with me a paperclip, metal paperclip, because that's what I often use in the classroom to illustrate fatigue. If you take a metal paperclip and you sort of bend it like this, and then you bend it back, you bend it like this, and then you bend it back. Eventually it starts out being smooth, but then you can feel it getting rough. What's happened there is that a crack has initiated. And then under cyclic stress, that crack will grow. And as you know, those of us who have played with these things know, after a while, then it will just break. So it's a very serious failure mode, and it was a serious threat to aerospace engineering. After those 3 accidents, everybody suddenly realized, oh, this is a serious problem. We have to figure this out. And a huge amount of money was spent to understand fatigue in the 1950s and the 1960s. And so fatigue is probably the best understood failure mechanism. And engineers now know how to control fatigue and to plan for it. So that's the first thing that happened to make our aircraft safe. The other is a change in design principle. Aircraft today are designed to be fault tolerant. What that means is you can have an aircraft with actually quite a few cracks in it, and it'll be perfectly safe. The cracks get dangerous when they get big and there's lots of them in one place. That's when you can have a problem. But the engineers know how to protect against that. And that's why there's very few fatigue failures anymore. Because they know where to look, they know where the stresses are, and they look periodically. If they see a crack in a commercial aircraft, it has to be replaced immediately. It has to be fixed immediately. As I say, they know when to look and they know where to look to keep these things from happening now. There's stories behind all of these, but I'm going to focus on some others, particular disasters, again, that had statistical content as well. And in all of these, well, first of all, most of them have been well documented again. And you can go to the internet and find a lot of information about them. In some cases, there were government reports, big, thick reports that were written about what happened. And I'll reference those reports as I go through and discuss these particular reliability disasters. So these are the 7 that I sort of written down as ones that I'm going to be talking about here this afternoon. A couple of these problems arose because of something called accelerated testing that was done incorrectly. Accelerated testing is a very popular way for engineers to get reliability information quickly. So this is kind of a cartoon to illustrate the basic idea. The basic idea is to test units at some high level of what we call an accelerating variable, sometimes referred to as a stress. So you can imagine an adhesive. And the product's okay as long as the adhesive is working. But over time, adhesive will lose its strength. And when the adhesive strength gets to be less than the stress, there'll be an adhesive failure. Something will come apart. So if you're designing something that's supposed to last 20 years, how can you be sure the adhesive will last 20 years? So the typical way to do that is to test at high levels of temperature, because the chemical reaction that causes the adhesive to lose its strength goes faster at higher temperatures. And so engineers can get information much more quickly. So this is to denote the end of the test, about 1,000 hours, about 3 months or so. And so a lot of units failing here, still some units failing here, and a few units failing here. We build a model. This is a statistical model. We estimate then the fraction failing at some use conditions, like 50 degrees C. So that might be the environment in which this product is working. And so what we have here, this line says this is the time at which 10% fail. And this is about 1 year here. This is about 10 years. So we go about 10% failing in 10 years. That's probably okay for some products. And so that's sort of a happy picture of an accelerated test. But some of the disasters I'll talk about were accelerated tests that were done incorrectly or interpreted incorrectly. Okay, there's lots of what we call pitfalls in accelerated testing. A great deal of caution is needed. Just in the last hour, I was having a discussion with several people about these kinds of tests. And why is it dangerous? Well, if you look at an elementary statistics textbook, when you study regression analysis, which is really what we do here, there's often a statement that says you cannot extrapolate. Okay, that's what you see in Stat 101 books. You cannot extrapolate. But guess what? In accelerated tests, we have to extrapolate. And that's what we're doing by extrapolating down here. So that's one of the pitfalls. I'm not going to talk anymore. Well, some of the pitfalls will show up, but I've co-authored entire papers, 2 of them, on pitfalls because, as I said, there are many of them. But that's a subject for a different talk. Okay, this is my first example. This is what's known as a AT&T round cell. And we used to call it the Bell cell. In sort of the early part of my career, I spent 15 summers working at AT&T Bell Laboratories. That's it was the research part of a very big telecommunications company. And until 1984, AT&T owned almost everything connected with telecommunications. In our homes, if we had phones, they owned the phone. They owned the wires in our house. They owned the wires for our house, from our house to the central office. They owned all the long distance lines. They owned everything. And they owned the manufacturing. And in the main offices where they have all the switching systems that send the, your call comes in and gets routed someplace else, all that equipment is and was powered by what we would call today an uninterruptible power supply. So if the power goes off, these batteries that they would have, made up of many of these cells, would take over. Just like if if the power goes out, your laptop still works. Why? Because there's a battery there. Same thing, same idea here. And if the power stays off for more than 5 minutes, then the generators come on. I see you have a generator out here in case your power goes off. Well, AT&T had the same things, because the reason they were allowed to operate as a monopoly, well, monopolies are really against the law in the United States, but they were allowed to do it because they guaranteed high reliability. And that was one of the tools. Now, in our automobiles, we have rectangular batteries, right, that start our cars and power our cars. And that's the kind of batteries they used to have in the main offices. But in the early 1970s, engineers and scientists at Bell Labs said, we're going to design this new battery that will last 10 times longer and have low maintenance. And they called them the round cell. Sort of like, you know, our flashlight batteries are sort of round. This is like the same thing. It's about this big around, and then they have 3 different sizes. They got a small one, a medium one, and a big one. The big ones carry more, or provide more current, would last longer. And each of these batteries would have 2 volts. And then they put them in series, and they would get up to 24 volts, which is what our telephone systems work on in the United States. So this is a revolutionary new design that was going to be guaranteed to last for 70 years. They did an accelerated life test and concluded these batteries are going to last 70 years instead of 10 years. Now, I remember back, I still remember, you know, some of these things, some things that happen in your life, they just stay with you. You can picture the whole thing, right? Other things I forget. I'm old, I forget a lot of things. But I remember this. I was working at Bell Labs in the summer. The traffic in New Jersey is worse than the traffic in Cochin. Maybe not as bad as the traffic in Bangalore, but it's bad in the morning. So I used to get up really early in the morning before the traffic to go to the office, because I don't like to sit in traffic. And I was sitting in my office, and then it got to be about 8 a.m., and everybody else was coming in. And there was all this talking in the hallway, lots of people out there talking. So I stepped out of my office to see what the problem was. The night before, there had been in Chicago a tremendous electrical storm with lots of lightning and so forth. And the power went out. And the backup system failed. The whole long-distance operation there in Chicago stopped working. That had never happened before because of the high reliability. And when they looked inside, you know, the next day, they said, what went wrong? Why did this fail? The positive, this is a lead-acid battery, just the same technology we use in our cars. And so this is a lead post. The post had totally corroded away. And they looked at the next one. Post is gone. A totally unanticipated failure. So this is what had been promised. And there have been hundreds of thousands of these installed across the United States and the world during the 1970s. And that night with the big storm was 1978 in July. And the root cause, ultimately, they figured out 4 years later. You know, after 4 years of intensive work, they figured out the problem. The root cause of the problem was that they had an epoxy seal. So here it says post seal. It's an epoxy seal that went around the lead. And there's a lot of chemistry going on in lead-acid batteries. And they did an accelerated test, but they never saw that problem. They never saw that problem in the accelerated test. Why? Because it turned out when they accelerated the test by turning up the voltage, that stopped the chemical reaction. You know, because the way you test a battery is charge, discharge, because that's the way we measure lifetime. How many charge, discharge cycles? Like in your laptop and your cell phone. That's how we count. My cell phone battery lasted for 8 years. Why? Because I never turn it on unless it's plugged in. So my batteries last a long time. My wife's battery, on the other hand, she never plugs in unless it's convenient. And she has it on all the time. She always says to me, you can always get a hold of me. I can never get a hold of you because your cell phone's not on. So I said, I'm saving my battery. Okay. So a large proportion of the batteries had to be replaced. Interestingly, so I was involved in a survey that was done that summer to figure out how bad is this problem. And then my colleagues there and I had to analyze the data, survival data. How long they've been in service, what's the state. And one of the things we learned is that 30% of the batteries had zero corrosion, even though they had been in service for a long time. It took the scientists 3.5 years to figure out why. What's the difference? And one of the key ideas there in engineering reliability is don't just look at the bad ones and try and figure it out. Look at the good ones. And so when they did that, eventually they figured out that the good ones, it was supposed to be a pure lead post. The ones that didn't have corrosion had a little bit of tin mixed in. It was a contaminant. Just happened to be left over. Because often making alloys, they mix a little bit of lead and a little bit of tin, or they mix lead and a little, but it wasn't supposed to be there. The design said pure lead, and that corroded with a little bit of tin. Everything was happy. Okay, so what did we learn? Unanticipated failure modes can have serious consequences. This cost Bell Labs millions and millions of US dollars. Accelerated tests can be misleading. There was an article that was published in the Bell Systems Technical Journal predicting 70-year life for these things. And here they are after 4 years failing all over the place. So accelerated tests are typically designed because you say, here's a failure mechanism. I want to accelerate that failure mechanism. But if you don't know about the failure mechanism, you probably won't accelerate it correctly. And also, as in this case, attempts to accelerate one failure mode can inhibit another. So it's really important to understand all the things that can cause your product to fail. And if the engineers had done more experimentation with different levels of voltage, they would have discovered this, but they didn't do that. They took a shortcut. Here's another interesting example that really is a case study. Indeed, there have been written case studies about this. Very serious reliability disaster that occurred at General Electric. I've had a long association with statisticians at General Electric, but everything I'm going to tell you about is in this article that appeared in 1990. So the story goes something like this. Jack Welch was the CEO of General Electric from roughly 1980 until roughly 2000, 20 years. Very famous person. Indeed, if you go over to Bangalore, there's a GE research lab there called the Jack Welch Research Lab. And he really, well, one of the things he did is he came into GE, and GE has all these companies. At that time, it was aircraft engines, and then they had space division, and the nuclear division. They had all these different parts of GE. And Jack Welch told all the heads of the companies, he said, you need to be number one or number two in your industry, or I'm going to sell you off. And he did. He ended up selling off a lot of parts of GE because he said, I don't want to manufacture commodity products. I want to manufacture products where we can make high profit. And we're going to have high reliability, high quality, and in specialized things, we want to be number one or number two. So that's what he told his people. Well, GE Appliances was having some difficulty. They were losing market share to offshore competition, particularly in Japan, like in their refrigerators. And they said, we need to do something. And so the engineers, GE has a lot of very smart engineers today and back then. And they said, we're going to design a brand new, high efficiency, lower cost rotary compressor. So rotary compressors had never been used in GE before. They used something called a reciprocating compressor. It always had. They've been very, very reliable. But they were big, costly, and not very efficient. But the theory said the rotary compressor would be lots better. And so they designed this, and they did an accelerated test. They took a large number of these compressors, and they ran them continuously. Usually a compressor maybe only runs 10–20% of the time during a day. But they ran them continuously in a warm environment, like a hot room, where they get the temperature up to maybe 36–37 degrees C. That's an accelerator as well. And they run them continuously. And after 1 year, they had 0 failures. They said, okay. And they had sort of a rule of thumb that said, that's going to translate into 10-year life. Okay? So they said, we're ready to go to market now. And so they did. And by 1987, they had put into service more than 1 million of these units. And customers loved them. So there were other features of the refrigerator. For example, this is the first refrigerator where you could get ice out of the refrigerator without opening the door. You just push a button on the front. Or you could get ice water, very cold water, without opening up the door, things like that. The customers really, really liked. However, they had a failure after just 1.5 years in service. And they went out and said, oh, what happened? So this refrigerator that failed was in Philadelphia. And when they went to investigate, they found out that the refrigerator had been installed in a closet. You don't want to put a refrigerator in a closet because it gets warm in the closet and the refrigerator runs continuously. So it was like an accelerated test. So they explained it away. They said, oh, well, it's, after 1.5 years, maybe that's like 15 years. We're okay. A couple of months later, they had their second failure. The second failure was not in a closet. It was in Puerto Rico. And the climate in Puerto Rico is a lot like coke shit. It can get hot many, many months of the year. But a product needs to be robust to that. And then they got serious. They said, uh-oh, maybe we've got a more serious problem here. And they dug in and they figured out that we've got a really serious problem here. Every single one of these 1 million plus compressors is going to fail prematurely. So huge warranty costs, but even worse is General Electric is very proud of their reputation for high quality, high reliability. And you're going to have all kinds of customers talking about this, market share is going to go down. So they made a decision. To proactively replace these compressors before they fail. So they're calling up their customers and saying, we have to come repair your refrigerator. The customer says, oh, there's nothing wrong with my refrigerator. No, we have to come repair it. And so they ended up buying compressors from a different company and then installing these so that they would prevent the failures. So it cost GE $450 million US That's a huge amount of money. I was thinking about this last night, and I was going to translate that into rupees for you, but I'm afraid the math's too complicated for me. But it's a huge amount of money. And if it had been any company by itself, the company would have gone bankrupt. But this was GE. GE is a big company. Appliances was one small part. And Jack Welch made the decision, we're going to protect our reputation. And so he did this. So what went wrong? Well, they rushed to market, for one thing. This is a new technology, and there were other competitors that were trying to do this as well. But if you've got a new technology, the first one to market has a huge competitive advantage. They did an accelerated test, and it turned out that after the test, the engineers did the right thing. They took the compressors that had been running for a year without failure, and they broke them down to look at them inside to see what they could learn. And what they learned was that there was a lot of discoloration because of a lubrication issue. These units had survived a year, but they were very close to failing. And that rule of thumb that they had, this isn't in the article. My good friend Wayne Nelson at GE, worked at GE at the time, he told me this. He said that rule of thumb that they had was wrong because they didn't test it. It was just a rule of thumb that had been passed down. So they thought they would have 10-year life, nothing close to that. So maybe the factor was 2 or 3, but not 10. The other thing is that the engineers knew about this, and then they told their managers, but that information did not flow up management. Why? Because it was well known that when mistakes got made at GE, Jack Welch always fired people. So there was a barrier to information flow. And that was the most serious mistake that they made that caused this problem. And I can tell you, when Jack found out about the problem, a lot of people got fired. This next example is a very famous reliability disaster. So the space shuttle was a huge program in the United States running over more than 20 years, where the early space flights, you went up and you went down and everything got thrown away. The idea of the space shuttle is you have one aircraft and it will make multiple flights into space. And the whole idea is to shuttle stuff up to the space station and do it in an economical way. And there's been 2 serious accidents where the entire crew perished. I'm going to talk about one of them. There's interesting stories about both, but this is the one that has some very interesting statistical content. So, I said I don't read my slides, and I usually don't, but read this because it's important. So this is the night before the accident. The night before the accident in January. So this is in Florida. And Florida has, again, I often think of Cochin and Florida having similar kinds of climates, but this is a little different because Florida in the winter sometimes you get really cold, meaning below 0 C. Not much below 0, but around 0 C, so you can have freezing and so forth. And there was this discussion between the NASA engineers and the Morton Thiokol engineers. So Morton Thiokol is a company that manufactured the rocket engines that were used to do the launch. Okay? And NASA, of course, is the manager of the whole space program, or was at that time in the US. Now in the US there's a lot of commercial space people doing it, because commercial can do better than government, is what a lot of people say, and I think in reliability, there's a lot of truth to that. That's another story. Okay, anyway, they were predicting -1 degree C temperature for the next morning when they were planning to do the launch. The previous low temperature of all 24 flights had been 12 C. That's a huge difference. And the discussion was, some of the engineers were really concerned that there could be a problem doing the launch at low temperature. They have no experience down there, and the experience they have suggests that there could be a problem. Okay? So Richard Feynman was a very famous physicist and very well known. And there was a committee, after the accident, there was a presidential commission that was put together very, very quickly to try to figure out what the heck went wrong here. And Richard Feynman, after the report was nearing completion, Richard said, I want to have my own, there was some disagreement about what to put in the report. He said, I want to write my own appendix. And so he did. And again, you can find these things on the internet. And what Richard noticed was that, from what they learned during the commission, is that the range of risk varied from 1 in 100 to 1 in 100,000. You know, so here are scientists and engineers saying, what's the probability of a disaster here? And so the manager's saying, nothing to worry about, 1 in 100,000. The engineers are saying, no, it's more like 1 in 100. I'll give you the punchline. When a proper analysis of the data was done, the risk is more like 1 in 6. Very high risk. And that's part of the statistical story that I'm going to tell here. So after discussing all the data that they had in front of them, the engineers said, do not launch. But then the NASA people put a lot of pressure on the managers at Morton Call saying, we really want to launch. And you said it's only 1 in 100. I mean, 1 in 100,000. If it's only 1 in 100,000, there's no risk. So, after getting that pressure, the Morton Call managers went against the engineers and said, yes, you can launch. Because NASA wouldn't launch unless Martin Call signed off on it. But as I said, in a subsequent careful analysis of the data that was available before the launch, and this was published in a statistics journal, they did a very, very careful analysis of all the data, and they concluded 1 in 6 with some confidence interval. So this
How was
is
that number, right? 1 by 100 and 1 by 2. How was it with them? They didn't have any analysis.
yeah, they didn't do it right, and I'll give you an idea about that in a moment. So this is a diagram, an artist diagram of the space shuttle. So there's 4 components here. This is a rocket engine, solid rocket engine. This is a solid rocket engine. These two things are basically the same on either side. And then this is the space shuttle. And the space shuttle has 3 more rocket engines down here. And if you're going to take off, you need a lot of lift power. And so all 5 engines are working very hard to get them off the ground. And then these 2 things fall off because their fuel's gone. And then this is the external tank. So these are solid fuel rockets. This is a liquid fuel rocket. The liquid being liquid hydrogen, liquid oxygen. No, they call it liquid hydrogen, which of course is highly flammable, and then an oxidizer. I'm not sure exactly what they meant by oxidizer, but it's oxygen basically. And then they mix those, and that's how a liquid rocket engine goes. And so these were running off the fuel in this tank. And this part was replaceable. That would fall off, they would pick it up and they could reuse it. They would also pick up these things. I don't think they reuse those, but they looked at them very carefully, see how did they go, what information can we get, and then this would go on into orbit around Europe. So that's the way the space shuttle worked. This is where the failure occurred, right here. Okay. So what happened? This is a quote from the Presidential Commission. A combustion leak through the right solid rocket. So this is the solid rocket, this is the left solid rocket, this is the right solid rocket. In the rocket aft field joint, so aft means the back of a boat or a plane. So there's the aft, so there's these seals here. So when they put the rocket together, they put these parts together. Okay, so each one of these, here's a part, they sort of fit together, and then there's rubber O-rings here that seal so fire can't get out when they're exploding. That's the idea. And it's a redundant seal, there's two of them. So after ignition, we can penetrate the external tank. So there was a failure here where basically fire was coming out and the fire got into this, and then that's what caused the failure. They emphasized it was not an explosion, it was more that just bad stuff was happening, and so they couldn't control anything anymore, and then it eventually just broke apart. So structural breakup is what they call it. At each field joint, so these are the different field joints. At each field joint, there's two O-rings, rubber O-rings. If the first one failed, it would be okay. But if you have two failures in the same place, remember I said like cracks? You can have lots of cracks, but if you've got lots of cracks in one place, that's a problem. And so in January 1986, both failed right there. That was the problem. So here's a picture. So you can see where the failure occurred right here. There's just a little bit of fire coming out. So this white thing, this is the big tank. That's the big tank, and here's the solid booster here, solid fuel. And you can see it breaking up here. The plume is getting bigger and bigger, and when that stuff's coming out, basically everything just came apart. So the root cause, as I said, was both O-rings failed. So during that telephone call, the engineers and the managers were discussing data. And this is the kind of data that they were looking at. I think somebody said there was 12 or 17 slides that they had faxed back and forth. This is before the days of email. So they're sending faxes and then they're talking about it on the telephone. So it's before the days of WebEx and other meeting places like that. And so they're having this conversation, and this is kind of the form of the data. So what we're looking at here is the previous failures that have occurred. These are the previous failures, and then this is the ambient temperature. And these are degrees F. I did a little translation at degrees C to make it easier to think about this. So this was the coolest one that had happened. And then these are temperatures at the O-ring. Weather. So this is what they're looking at. What they didn't do was graph the data. That was the first mistake. So if you graphed the data that they looked at, the data, I want to emphasize that, the data that they looked at, this is what they would be seeing. Okay, so here's 12 degrees. This was the coolest one where they had had a failure in the past. And most of them you can see were up here. These are just the failures. And so this is the coolest one. This is the one at 12 degrees C. And they had 3 O-rings that failed. But they were different places, so no worries, right? But 3 failures. And I can imagine the engineers saying, well, look, 3 failures, and that was because of the low temperature. And then I can imagine one of the managers saying, but look, you had 2 failures here, and it was hot. or at least very worn. So they're arguing back and forth about this. Where did the numbers 1 in 100 come from, or 1 in 100,000? They were looking at these data, but there was no sophisticated analysis. It was just what people said in the meeting. The other serious problem, serious statistical problem, is that they ignored, and there's where we're extrapolating. So there we are, extrapolating again. So we've got data here, but we're extrapolating all the way down here to 0 degrees C. No experience down here whatsoever. But the other serious problem is that the data ignored all of the times where they had launches with 0 failures. They thought the 0 failures were irrelevant. But the 0 failures at high temperature say few or no problems here. But they never had any 0 failures here. They're always getting failures when there's cold temperatures. And so the correct analysis used all of these data and basically did a logistic regression. And that's how they predicted the failure of the O-rings. And then they look at it, so there's a redundancy here, series system, and that's where they came up with the 1 in 6 as the risk. So very serious problem here. So engineers knew the launch was risky, but they didn't have the skills to convince the managers. Managers thought that they knew 1 in 100,000, but they didn't know. Proper graphical analysis of data is really important because that's how you can convince people. You put the information into a graph and you don't have to spell out formulas. You can make it crystal clear. And you need to use all of the relevant data. That was the big mistake. And be very concerned when management overrules engineers. So, that happens a lot. Engineers tend to be conservative. Managers tend to ask, are we being too conservative? Because it costs money to be conservative. Okay, this is a very famous aircraft accident known as United 232. If you ever fly on United Airlines, you'll never fly on United 232. They retired that number because of this accident. So, there was a DC-10, doesn't say that here, but it was a DC-10 flying from Denver to Chicago, and they got over the western part of Iowa, a few hundred miles from where I live, and there was what is euphemistically called a disk separation. Basically, the aircraft engine exploded, causing a failure of the hydraulic system, even though there was triple redundancy in that system. In that accident, 110 passengers and 1 crew member died, but miraculously, 175 passengers and 10 crew members survived the accident. I'll explain how that happened in a moment. So it was a McDonnell Douglas DC-10 and a General Electric engine. And all the details that I'm talking about are documented in an NTSB report, as we call it. Whenever there's a big accident like this, there's always a careful study run by this government agency to get all the information to try and prevent it from happening again. So this is what a DC-10 looks like. There's 3 engines, 1, 2, 3, and it was the number 2 engine that exploded. And when it exploded, it's what's known as an uncontained disk separation, so that the engine has a cover. And if you break a fan blade, that's supposed to be contained. But that happens more frequently. It's still a serious problem when it happens. But this was the whole disc in the middle of the aircraft that failed. So here's what the disc looks like. Here's what a fan blade, so there's fan blades all around here. When you look at the front of an aircraft engine, you see those big fan blades. That's what we're talking about here. And this is the disc. But when the disc explodes, it's so big and heavy and massive that it just went outside the containment. And in the tail of the DC-10, you have the hydraulics that control the rudders and the other things back there. And they had 3 different hydraulic systems. But the hoses were all together. And so when it exploded, it severed all 3, so there's no hydraulics to control the aircraft anymore. Fortunately, there was a pilot who actually did work for United, and he said, I think I know what we might be able to do. And so he actually took over the controls, and he was able to steer the aircraft by using the other 2 engines under the wing. By just controlling the thrust, you could move the thing around, and so they flew around for a long time until all the fuel was gone, and then they did a crash landing in a place called Sioux City, Iowa, at a relatively small airport. And it was a crash landing. As I said, a lot of people perished, but a lot of people survived as well. So the root cause was a fatigue crack, known as a hard alpha. So I said before that in fatigue, engineers really understand fatigue. What I mean by that is once they know the size of a small crack, they can predict very precisely how fast that crack will grow. They can't really predict when that crack will initiate. That's where all the variability is. But once you've got an initiation, fatigue is pretty well controlled, especially in commercial aircraft. Because every time an commercial aircraft takes off, it follows exactly the same regime in terms of stresses and everything. Okay, and so what happened is that cracks are supposed to grow at a certain rate, but when it hit this brittle part, it went very quickly. And that's when the disc exploded. Unfortunately, that defect was not detected, even though they know these defects can arise, and they inspected it many, many times. Well, I think 3 times during manufacturing and once in service. And they never detected the crack, even though they should have detected it. I can tell you that since then, and this is part of my direct involvement, since then there's been a huge amount of effort during the 1990s, especially, to study inspection of these kinds of parts. And today, the inspection procedures are much better than they were then. So there were some problems with GE's manufacturing inspection and record keeping. It turned out that there were 2 discs with the same serial number. And nobody could really explain why, except it was a mistake somebody made. So these are all conclusions from this report. And then poor design of the hydraulic system. And as I said a moment ago, the accident led to many improvements in both manufacturing and inspection. So the probability of this happening again today is pretty small. So, better inspection. So these are basically recommendations from the report. Better design sources for power and engine controls. Need for better long-term record keeping, that was a GE problem. And a worldwide database, anytime one of these parts fails, now is a requirement, any place in the world, that that information will go into a database that then can be used to do these predictions. So, I guess I'm out of time. Let me take a few more minutes, because this is another really interesting example. This is very well known Ford Firestone reliability disaster. So Ford and Firestone have been cooperating for 80 years, where Firestone would manufacture the tires and Ford would manufacture the cars and buy the tires. But in the late 1990s, there were reports of what are, again, euphemistically known as tread separation events. And these things reports started to come in, particularly in warm environments. And a tread separation failure at high speed, your tire literally blows up and comes apart, can cause a serious accident, and did cause many serious accidents. In the United States alone, there were 271 deaths from these accidents caused by the failure. And they're much more prevalent in warmer, hot climates because temperature accelerates certain kinds of failure mechanisms, just like an accelerated test. In August 2000, Ford made the decision to recall 14.4 million tires to prevent these accidents from happening in the future. So, Firestone blamed Ford, and Ford blamed Firestone. So, how to resolve this? Well, led by Tim Davis. Tim Davis is one of the world's, of this generation, best statisticians working in industrial problems. And Tim was a Ford statistician. And he was working on many things before this happened, including Taguchi methods and robust designs. We integrated all those throughout Ford, and it had a really positive influence on their quality and reliability. And when this problem arose, Tim was put in charge of figuring out what was going on. Interestingly, Tim, early in his career, worked for a tire company. He knew tires, and he knew how to test tires. And when this started happening, the Firestone managers told their engineers, don't talk to anybody at Ford, because everybody's afraid of lawsuits and so forth. So then they were sort of going to battle after cooperating for so many years. So the next 4 slides I'm going to show you come from a presentation that Tim Davis wrote. So I've talked to Tim Davis about this. We've been talking about it since the beginning, because as I said, I'm a student of these things, and Tim knew a lot. And there's a lot you can read about this, including a government report. But Tim can tell me a lot of things that's not in the report, and I'll say a few of those. And he sort of hints at them here. So he calls them subject tires. These are Firestone tires. And this is something called cumulative hazard. Some of you know what that means. So basically, if the cumulative hazard is a straight line, if it's linear, that means your risk is constant over time. But when we see the cumulative hazard going up, that means it's a wear-out failure mechanism. Your propensity of failure is getting worse and worse over time. You've got a brand new tire, you're probably okay for 100 miles or something, or 100 kilometers or something. But over time, that risk is going to go up. That's what this picture says. These are the Firestone tires. The 3 different colors here represent 3 different factories. So you can see this is a process out of control. Something's not right at these factories. And these are other manufacturers. So these are field data, based on field data. So there's something seriously wrong with Firestone tires here, because this is where you should be. Notice the risk is 10 to the minus 6. These are very low risk events, especially early in life. And most of us don't keep our tires for 10 years. They wear out before that, right? Some people don't drive a car very much, and then their tires might last 10 years. So pretty low risk here, but very high risk here. So that was the first hint. Then looking at what is the cause. So here's the tire, and there's different layers in the tire. And so there's the outer layer that has the tread. And then there's a separator here, and the distance between them is called the wedge. And this is the size of the wedge for Firestone tires, the size of the wedge for other tires. So again, Tim didn't say that, but the subject tires are Firestone. And so the wedge is much smaller here and much larger here. What happened is Firestone made a change to the design of their tires. They narrowed the wedge, made it smaller. Why? What do you think? Cost savings. They're trying to save money. I used to think when engineers make a design change, they're trying to improve reliability. Usually when they make design changes, they're trying to reduce cost and maintain reliability. And when you make such a change, it's really important to do tests to make sure that you didn't reduce the reliability of your product. But the Firestone engineers didn't do that, or at least they didn't do it correctly, or they would have discovered what Tim discovered when he did his test. So again, all of this is field data. Remember, they had lots of recalls coming in, so they had lots of tires that they could take apart to see what are these dimensions, and this is what they saw. And then here they're just doing some tests of when you pull the different parts of the tire apart. That's what's happening here. So they're pulling apart here, and then they're looking at age, and they're looking at strength of the adhesive. Okay, again, the adhesive is what's holding these parts together here. And what Tim told me is that when they reduced the dimension here, the stresses were higher, and the degradation went faster because the temperatures got higher as well. And that's what they're seeing here. Again, these are the good tires where the strength is high. These are the good ones where the strength is high. These are the Firestone where the strength is low. I said no formulas, but I couldn't get rid of these formulas that Tim had on the slide, so those are my formulas. Then Tim did some experimentation in the laboratory. He knew how to test tires, and the red circles here, so there's three dimensions: load, pressure of the tires. You know, when you fill up your tire with air, there's a certain pressure there, that's what that pressure is, and then ambient temperature. So he did these tests in the laboratory, and he discovered that in the red places here they had failures, the green ones no failures. So this confirmed what they saw in the field data, and confirmed that the problem was a Firestone tire problem, not a Ford problem. So one thing that was learned in this whole problem is that careful surveillance of field data can detect these problems earlier. They waited too long here because Firestone and Ford weren't reporting these things when they happened, because they knew that would hurt their sales. And they weren't ready to do the recall yet until the information became overwhelming. In the United States, there now is a law that says when you have these kinds of failures, they have to be reported in a short period of time. And the whole idea is to discover these things quickly. Proper statistical analysis of the field data combined with careful experimentation can confirm the cause of failure. The field data suggest, but cause and effect, the experiment is what nailed that down. And then I said this a few minutes ago, if you're going to make a cost-cutting change, you really do need to do adequate testing to make sure you didn't hurt the reliability. The Firestone engineers apparently didn't. Okay, I'm going to pretty much skip over these two examples. I'll just say there was another huge debacle of electrolytic capacitors in PC motherboards. So I've talked to engineers and statisticians at 3 different companies who all told me we weren't the only ones. Everybody suffered from this in the early, mid-1980s. So I talked to engineers at IBM, HP, and Dell. Actually, the Dell engineer came to me and said, it was our IT people and the Dell people, and they said, we've got this problem, and we want to figure out which computers to proactively replace in our big customers. So can you help us figure out which ones to replace? They called me a month later and said, we're going to replace them all. No, we're not going to replace them. We're going to wait until they fail, and then we're going to replace them because all of them are failing. All of them are going to fail prematurely, just like the rotary compressor. But Dell did the right thing. They took their 3-year warranties and they extended them way out until a certain date. They said after this, they added like another 3 years. So you could keep your computer for 6 years at the minimum. And if you bought it earlier, it'd even more than that. And they would replace your motherboard if it failed. So they figured that most people get rid of their computers after 4 or 5. I don't. I keep my computers. But that was what happened there. There's been a number of battery problems. Sony is sort of a famous one. So here's some people sitting at a conference and the laptop just blows up. And there's movies of these things on the internet that you can find, on YouTube and so forth. We've heard about the Samsung 7 that was blowing up for a long time. They wouldn't let us take those on airplanes. And I don't know how they enforced that. They said, well, if you've got a Samsung 7, you can't get on the airplane or something like that. I don't know if they did enforce it or what. So these are the references where I got most of my information. Lots of Wikipedia stuff. This is the very famous paper about the space shuttle. So these are 3 very good statisticians who did that work. So thank you for bearing with me for a few extra minutes. Some concluding remarks. Many reliability disasters are caused by unanticipated failure modes or a known failure mode and unanticipated acceleration because you don't understand the environmental conditions. As I said earlier, engineers tend to be conservative. But managers say, are we being too conservative here? I've heard it a number of times. There needs to be appropriate balance in making these decisions. And statistical and probabilistic methods should play a really important role in these reliability-related things because there either is a lot of data around or there should be a lot of data around to help make these decisions. And I got some advice on my slides from these people who reviewed it and gave me comments, so I appreciate it. Thank you very much for your attention. And I'd be happy to take questions if there's a little time.
Any questions?
Everybody is free to interact, please. Perhaps they would like it one-to-one.
And I'd be happy to do one-to-one too.
So the lessons I learned is we need to have engineers in an organization, engineers, managers and statisticians.
Yes.
That would avoid a lot of things.
Yes.
That makes us very important, right? So if there are no questions,